iterative methods have a very different way of the solution approach to the solution of a phi equal to b. You do not actually solve a phi equal to b. Let us just put a heading, iterative methods for the solution of linear algebraic equations. Our basic equation is a phi equal to b. We do not try to say that phi, therefore phi is equal to a inverse b. We do not solve this equation at all, but we solve another equation, phi equal to p phi plus q. So we write a phi equal to b in the form of phi equal to p times phi equal to q, and we solve this by successive substitution, which is also known as the Picard's method. Therefore we start with some initial guess for the phi, and we write a recursive relation phi k plus 1 is equal to p phi k plus q, where the k superscript here indicates the iteration number. And so we start with an earlier value of the phi, that is the set of all variables, that is the guess values, and then we go to the new values. We generate a new guess value, new values from this rephrasing of the original equation, and this successive substitution is said to be convergent if limit as k tends to infinity phi k is equal to phi. So that is, as the number of iterations increases, that is with successive and more successive substitutions, if the phi k tends towards a fixed set of values phi, then we say that this iteration is convergent, is a convergent scheme. And we hope, okay, when the method is correct, that the converged value is the solution to the original equation. So this particular the approach, and typical iterative method follows in this way, that from the given a phi equal to b, we rephrase it as phi equal to p phi plus q, and from this we generate a recursive relation which enables us to go through, from an initial guess, go through a series of ever improving values which will converge towards the final solution. And this method, any iterative method, is characterized by three quantities: by how to construct P and Q, from given a phi equal to b, what is the condition for convergence, condition or guarantee for convergence, and what is the rate of convergence. So the idea is, it is not sufficient to be able to get P and Q from A. For example, we can write A equal to some P plus Q and then try to make an arbitrary division, and but the resulting iterative scheme must be convergent. Okay, so under what decomposition of A into P and Q will we have a convergent iterative scheme? It is not sufficient to have a convergent iterative scheme, we would like to have good rate of convergence. if we are dealing with a linear equation, then the choice of the initial guess, initial vector phi naught is not important. But if it is a nonlinear equation that we are trying to solve, okay, we are said it is a linear equation, but we have nonlinear equations as part of our discretization of our Gaussian equations. If they are not linearized, so if you are dealing with a nonlinear equation, then the choice of the initial guess may also be important, but otherwise for linear equations it is sufficient to be able to construct P and Q from a given A and B, and also we need to find out under what conditions this would converge, and we should also importantly find out the rate of convergence, so that we have an estimate and also an assurance that we will soon be getting to the converged solution, because an iterative method is a way of generating successive improvements, and improvement is never final, it will go on to the end, okay, until we are defeated by machine accuracy and things like that. Okay, so in that sense the method of approach for an iterative solution is different from the method of approach for a direct method, and because we are getting an ever improving solution for a convergent scheme, provided we have come up with a P and Q which is which guarantees convergence. Okay. So provided we have that, we are going to get an ever improving solution for phi. Okay. So in such a case, that means that we can stop the iteration at any time. We have already some guesstimate values for phi, and this will be useful in the context of our CFD type of solution, where we take account of the coupling between the x momentum equation, y momentum equation, z momentum equation, and the pressure correction equation or pressure equation, continuity equation. So these kind of couplings are done by effectively by another Picard type of solution, where you solve AU equal to B and then AV equal to B prime, and then A double prime W equal to Q, like that. Okay, so each time you solve for one of the variables, assuming the values of the other variables. So in that case, you are already starting with guessed values of V and W when you solve the x momentum equation. So you solve the x momentum equation using the iterative method until you get to some reasonable improved solution. You go to the y momentum equation, solve for V, and then you solve it until reasonable improvement, you go to W equation, and once you get this, then you can come back to the U momentum equation and then substitute the improved values for V and W and then go like that. So in the context of sequential solution of the x y momentum equations and the continuity equation, an iterative method which provides us an improving, ever improving solution as we increase the number of iterations is a good choice. For an iterative method to work, it is not sufficient to have a convergent scheme or one that has a good rate of convergence. It is also important that this construction of P and Q should be such that that does not require too much of mathematical operations. Okay. In addition to that, the P and Q should be such that the successive generation of solution, that is starting with phi k to get phi k plus 1, should not also involve too many mathematical operations, because we need to do this iteratively. So a successful iterative method is one which enables an easy decomposition of A into P and Q, or easy construction of P and Q from given A, and one which enables us to go from phi k to phi k plus 1 in a relatively easy way without too much of computation time, and one which has a wide range of convergence, especially of relevance to our type of problems, and one which also has a reasonable or good rate of convergence. Okay, so there are classical iterative methods like the Jacobi method and Gauss-Seidel method and the successive over-relaxation methods, and we would like to they share some of these features, and we would like to examine them in this context. So if you take, let us call this as basic iterative schemes, in all the cases A is written as m minus n. Okay, so the construction of P and Q is such that A is decomposed into the summation of m and n. So it is not a multiplicative decomposition like LU decomposition, it is a summation type of thing, and this implies that A phi equal to B will get converted to m minus n phi equal to B, or m phi equal to n phi plus B. From this we can construct, we can also write this as phi equal to m inverse n phi plus m inverse B. Okay, so when you put it, this becomes our P and this becomes our Q. Okay, so when you do decompose m into m minus n, then we have it like this. Typically we do not construct P like this and Q like this because that involves finding m inverse. Instead of doing the m inverse and then doing the product of these and these like this, we go directly here and then we can say that m phi k plus 1 is equal to n phi k plus B. So in these basic iterative methods we do not construct m inverse and then we do not multiply this, we write it like this, so that, and the solution of this is also very easy, and we will see how easy it is, so that not constructing m inverse and then putting it like this is not a disadvantage. Now what are these m and n? In the Jacobi method and also the Gauss-Seidel method, and the successive over-relaxation, this is also known as SOR method. These are classical methods for iterative solution of a matrix equation. In these, all the three cases, A is written as D minus E minus F, and what is the what are the three here? If you take, this is the A matrix, all the diagonal elements together constitute D, and all the lower triangular things except for the D constitute minus E, and all the upper triangular things except D will constitute minus F. So A is broken up into D minus E minus F. What this means is that finding the breaking up, the decomposition here is straightforward, because so you can write D to be equal to Dij equal to Aij delta Ij. So this identifies this delta Ij is the Kronecker delta when I is equal to 1, j equal to 1, then this is equal to 1. So this obviously identifies only the diagonal elements, all the rest will become 0. So our D is all the Aii, this is 0, this is 0, this is our D, and E is all the diagonal elements and upper triangular matrix is 0, and here it is minus Aij, in this part. So we can write Eij is equal to minus Aij if I is less than j and it is equal to 0 otherwise. And Fij is minus Aij if I is greater than j and is equal to 0 otherwise. So our F here is 0 here and this is minus Aij. So this decomposition is straightforward, it is just minus 1 times this, and even this we do not have to do this multiplication by minus. Okay, so with this the Jacobi method, okay, with this basic thing we can say in the Jacobi method m is equal to d, okay, this m here is equal to d and n is equal to minus e minus f. Okay, when we put it like this, so n is equal to e plus f, so that when you put m minus n, this becomes d minus e d minus f, and that is what this is. And this makes the equation like d phi k plus 1 equal to minus okay, we take it to the right hand side, so this is e plus f phi k plus b. Okay, so this looks somewhat strange, but when you actually write down the equations, then what this one is saying is that this is a11 phi 1 is equal to this, we are taking it to the k plus 1 is equal to, this is minus of this, so this is minus a12 phi 2 k minus a13 phi 3 k minus a14 phi 4 k minus a1n phi n k plus b plus b1. Okay. Similarly, we have a22 phi 2 k plus 1 is equal to minus a11 phi 1 k minus minus a21 phi 1 k minus a23 phi 3 k minus a24 phi 4 k plus so on minus a2n phi n k plus b2 and so on. So and let us just put one more, a33 phi 3 k plus 1 becomes minus a31 phi 1 k minus a32 phi 2 k minus a34 phi 4 k minus a3n phi n k plus b3. Okay. So these are the equations that we are actually solving here. So we can see that in order to get phi 1 k, all we need to do is that we do these computations plus b, and the whole thing is divided by a11, and in order to generate phi 2 k plus 1, we do each of these multiplications, add to that b2, divide by a22, and again here it is these multiplications and then divide by a33. So if you want to generate phi 1 and phi 2 and phi 3 and so on, 1 2 3 4 so many multiplications and one division for this, and again so many multiplications and one division for this. Now the advantage, especially in the context of a CFD solution, is that this is an equation which involves all the variables, but we know that in a discretized scheme only a few of these are non-zero. Okay, so if we retain only those things that are non-zero, then we can write these things very compactly, so that the number of multiplications here becomes very small. We can take advantage of the sparseness of the matrix. So typically for in a two-dimensional flow kind of situation, we have if we imagine this is the point here, then this is influenced by this point, this point, this point and this point. So this is what is coming on the left hand side, and these four are what are there on the right hand side. Okay, so the solution for this at k plus 1 is given by 4 multiplications of these 4 coefficients with the current values, okay, the estimates at the current values, plus the b1 or b2 like that, and division by this quantity here. So that means that each evaluation of the phi k here requires 4 multiplications and 1 division, 4 multiplication and 1 division, so that is 5 operations, and we have n such equations because we have n variables. So that means that to go from k to k plus 1 we need only 5n number of math operations. Okay, so we have made the point that you want to go from k plus 1 to k plus 1 very efficiently, and we can see that for a typical two-dimensional flow with this kind of discretization and computation molecule, we require only 5n number of mathematical operations to go to from k to k plus 1. If it is a 3-dimensional flow, we will have 2 more terms, 2 more things, that becomes only 7 times n. So to go from 2 dimensions to 3 dimensions, it hardly takes another 2n number of operations. So it scales linearly. This is as far as going from k to k plus 1 is concerned. So we can see that the implementation of the Jacobi scheme is such that the decomposition of A into m and n is straightforward, and the generation of phi k plus 1 from phi k is also very simple because it requires only 5n number of mathematical operations. So the next condition that we have to satisfy is it convergent, under what conditions it is convergent. We will see that when we do the convergence analysis, and we will see that this is convergent if we have diagonal dominant for matrix A, and the rate of convergence is also important, and we can look at the rate of convergence from when we look at some ideal cases, and so from that we can get some kind of estimate for this. Okay, now what about the Gauss-Seidel method? This is a Jacobi method where m is equal to d and n is equal to e plus f. In the case of Gauss-Seidel method, m is d minus e and n is f. So that this equation gets written as d minus e phi k plus 1 equal to f k plus b, and we can write the same thing as d phi k plus 1 equal to e phi k plus 1 plus f phi k plus b. There is only a small difference between the Gauss-Seidel method and this method. When you write down an equation which is similar to this, we can for example if we write down using the evaluation of A33 phi 3 k plus 1 in the Gauss-Seidel method, this will be equal to minus A31 phi 1 k plus 1 minus A32 phi 2 k plus 1 minus A34 phi 4 k minus A35 phi 5 k plus so on minus phi 3 n A3n phi n k plus B3. So, the evaluation, the implementation of the Gauss-Seidel method and Jacobi method, they look very similar. Here also you have to do 1 multiplication, 2 multiplication, third, fourth, 5 like that. So, if you have 4 non-zero components coming on the right hand side, we have to do 4 multiplications and division by A33. So, in terms of number of mathematical operations to go from k to k plus 1 for a particular variable, it is still 5 operations, 5 multiplications or divisions for in 2 dimensions and 7 in the case of 3 dimensions, and there are again n equations like that. So, to go to k plus 1, we again require 5n number of mathematical operations, the same number of operations as in the Jacobi method. So, it, even though we have made a different decomposition into m and n, it has not resulted in any increased number of mathematical operations per iteration. So, that is, the generation of k plus 1 solution from k solution does not require additional number of mathematical operations. The difference that we see is that if you are solving the third variable, the previously computed variables, that is phi 1 and phi 2, are approximated using the latest value, that is, by the time we in this sequential solution we have computed phi 1 and phi 2, now we are at phi 3. So, we have already got the improved estimate for phi 1 and phi 2, that is, we already have phi 1 k plus 1 and phi 2 k plus 1. So, we make use of those values here, and for those succeeding ones, that is from 4 to n, those variables are still the old values. So, we use them as k. So, that is, in the Gauss-Seidel method we make use of the improved values wherever they are available. So, if you look at for example the 9th variable a 99 phi 9 k plus 1 will be given by minus a 91 phi 1 k plus 1 minus a 92 phi 2 k plus 1 so on minus a 98 phi 8 k plus 1 minus a 10 okay 9 10 phi 10 k plus so on like this. So, up to 8 we make use of the new values, and after 9, that is from 10th onwards, we make use of the old values like this. So, in both the methods the number of operations required to go from n to k plus 1 is about the same, but the actual number of solutions to go to the converged solution will be different for the Jacobi method and the Gauss-Seidel method, because in the two cases the P matrix, that is, this is the iteration matrix, the iteration matrix is different for the Jacobi method and Gauss-Seidel method, and everything about this iterative scheme, that is, will it converge or not, okay, is it a convergent scheme or not, and is it, what is the rate of convergence, is determined by the characteristics of this iteration matrix. Once this iteration matrix changes, then these properties of the iteration scheme may change. So, it is not necessary that both these will be convergent for all cases, and both this will have the same rate of convergence. Okay. So, we can expect different rate of convergence for these two methods, okay, and different condition of convergence for these two methods, okay. But the end solution, because if both of them are convergent, we expect the end solution to be the same irrespective of what the initial solution is. That is the advantage from this. So the two methods are very similar and very easy to implement. In the case of the SOR method, successive over relaxation method, what we do is that when you go from k to k plus 1, this you have in this iterative method, this gives you this. So we have delta phi k, this is the improved value minus the old value, okay. So this is the improvement in the value of phi that you have predicted using this iterative scheme. So in the SOR method, you add only you add more than the predicted improvement in the case of over relaxation. So you actually say that phi k plus 1 is not equal to phi k plus delta phi k, okay, like this. You actually say that phi k plus some omega times delta phi k, and if omega is greater than 1, then this is called over relaxation, and if omega is less than 1, then this is called under relaxation. Okay, so this is the nature of this successive over relaxation. One point to note about this Jacobi method and the Gauss-Seidel method is, in the Jacobi method we are making use of the old values for all the computations, and here we are incorporating the new values as and when they are available. So what this means is that in the Jacobi method, the order in which these equations are solved does not matter, because this phi k plus 1 is generated from known values of phi k, whereas in this particular case, by the time you want to do phi 3, you have to know phi 1 and phi 2, and then in order to know phi 9, in order to get phi 9 from k plus 1, you need to have solved phi 1, phi 2, phi 3, phi 4 up to phi 8 using this. So this is a sequential successive calculation, whereas this is a simultaneous solution, okay. So you can say that this is a simultaneous evaluation, whereas this is successive evaluation, and this successive over relaxation comes from the application of the over relaxation parameter omega to this particular method, okay. So typically when we say successive over relaxation, we talk about the successive over relaxation or over relaxation of the Gauss-Seidel method. So this is also equal to GS SOR, effectively it is equivalent to that, okay. Let us see what form the SOR method takes on in terms of implementation. We are solving a phi equal to b using an iterative method, where we write m a as m minus n and construct an iterative scheme like m phi k plus 1 equal to n phi k plus b, and in the SOR method, A is, this is the general decomposition of the diagonal elements and the lower triangular elements except the diagonal, upper triangular elements except the diagonal elements here. This is the standard decomposition. We take D only in the case of, as M in the case of Jacobi method, and D minus C in the case of Gauss-Seidel method. If you are writing a Jacobi method plus SOR, then in that case m is written as d by omega, where omega is the over relaxation parameter, which has a value between 0 and 2, and n will be 1 minus omega times d minus E minus F. And in the case of Gauss-Seidel SOR, m is d by omega minus E, and n is 1 minus omega by omega times d minus F. So that when you now put m minus n, then this d by w here gets cancelled with this, and we get omega by omega times d. So everything becomes the same as this. So m minus n here is still the same as this one, except for the fact that in the implementation part we are putting a value of omega which is between 0 and 2. So if we write like this, we can substitute these into the corresponding equation, but ultimately we can show that in terms of the computation of phi 1 k plus 1 is written as a11 phi 1 k minus omega times a11 phi 1 k plus a12 phi 1 k phi 2 k plus a13 phi 3 k plus a1n phi n k minus b1, and a22 phi 2 k plus 1, we are looking at the Gauss-Seidel based SOR. In this case this is a22 phi 2 k minus omega times a11 phi 1 k plus 1 plus this will be a21 and a22 phi 2 k plus a23 phi 3 k plus so on up to a2n phi n k minus b2, and we will just write one more before we write the general expression. This is a33 phi 3 k minus omega times a31 phi 1 k plus 1. We already have, by the time we come to the third row, third variable, we already have phi 1 at k plus 1, and we also have phi 2 at k plus 1 plus a33 phi 3 k plus so on up to a3n phi n k minus b3. So this is how we can do this. Is this equivalent to the SOR method? If we put, let's just check the limits. If we put w equal to 1, okay, there is this thing becomes d minus e, and this thing becomes 0, so n becomes minus f. So when you put in this SOR, Gauss-Seidel based SOR method, if you put w equal to omega equal to 1, then you recover the Gauss-Seidel method. Now what will happen to this? If you put omega equal to 1 here, this and this cancel out, and this becomes b1 minus all these things, and here this will cancel out with this, and this becomes b2 minus all these things, and that is exactly the way that we compute these variables using the Gauss-Seidel method. So in that sense, this one, when you put omega equal to 1 here, then this goes back to the standard Gauss-Seidel method. Now when you put, we have also said that in an SOR method we write x k phi k plus 1 equal to phi k plus omega times delta phi k, and this is actually the form that we have used here, and we know that delta phi k is equal to phi k plus 1 minus phi k. So if you substitute that here, you get phi k minus of phi k minus phi k plus 1. Okay, so this phi k plus 1 is minus of phi k plus 1, for example, is this whole thing, and this is the phi k that we have here, and this is the minus omega that we have. So in that sense, this whole expression within the brackets is phi k minus 1, that is equal to minus of delta phi k, and then we have the minus omega parameter here. So this particular way of writing is consistent with the definition of the SR method, although it is a bit hidden when you express it like this. Now why do we write it like this? Because in terms of computation, if we look at these things, the number of additional computations that we have to do is very little. We have an omega which is multiplying all these things, and anyway we are doing all these things. It is only that a11 times this, but this anyway is going to be divided by this. So this equation can be written as phi 1 k plus 1 equal to phi 1 k, that is that when this divides this you get 1, so you do not need this multiplication. It is only one additional multiplication of omega that is required for this. So implementing the SOR method into the Gauss-Seidel method does not increase the computational time significantly to go from k to k plus 1. So that is why we have written it in this nice form, so that we can take advantage of limited number of computations that we have to do. So the point that we want to make here is the number of mathematical operations in terms of multiplications and divisions for Gauss-Seidel method and SOR method, or Jacobi method and the corresponding SOR method, is virtually the same. What makes the difference is as you go to from k to k plus 1, you have the same number of operations, but how many such iterations do we have to go? We have to go from k plus 1 to k plus 2, and then we put this back here, we go through this loop. So how many times we go through this loop depends on what is the rate of convergence, and that depends on specifically the parameter omega. So we choose the parameter omega such that the number of these successive approximations that we have to make becomes lesser and lesser, so that we can gain an overall advantage in terms of computation of the solution for a phi equal to b. So the SOR method would work if the number of iterations, number of successive approximations is decreased, and that by how many decreases depends on the choice of the omega parameter. So that is why one has to use the optimal value of the omega parameter, and at this stage, before we do anything formal, we can say that we have seen that the Jacobi method and SOR Gauss-Seidel method, the standard Jacobi and Gauss-Seidel, have number of mathematical operations capital N for a solution of the order of n square is what we have mentioned, and SOR method with the optimal parameter of omega. Okay, so that is that parameter, that value of omega here, which will reduce the number of these operations to the minimum that is necessary in order to achieve an accuracy, desired accuracy of evaluation of this phi, is such that this will vary as 1.5. the exponent is reduced from 2 to 1.5, and when small n is large, when you are dealing with a large number of equations, this change in exponent from 2 to 1.5 can be humongous. For example, if you say that n is 10 to the power 4, that is 10,000 equations, which is not much, then SR gives you a factor of 10 advantage in terms of computation time as compared to the standard Jacobi method or Gauss-Seidel method. So an order of magnitude increase in the speed of computation is possible if we use SR method, but this is true only for optimal values of omega. If we are suboptimal, as we increase the let us just make a schematic sketch here. N is the total number of mathematical operations to get a solution, and omega is the parameter here. Typically n may go down like this, maybe between 1 and 2 is typically the over-relaxation range, and at the optimal, so this is the optimal value of the parameter. So at the optimal value you have a large decrease in the number of mathematical operations which are required for this, and if you are, this is typically steep, so that if you are suboptimal, if you took a value of omega either like this or here, you would have much higher value of the number of operations. Okay. What is important is that we have to specify what the value of omega is in order for this scheme to work. So the parameter omega, the over-relaxation parameter, is an input to the scheme, and we have to choose it. For some theoretical cases, we can determine a priori what is the optimal value of omega, but for the general case, when you are talking about a general a phi equal to b type of solution, then we do not know the value of omega. It can be anywhere between 1 and 2, and there may be a difference between omega of 1.7 and omega of 1.6 and omega of 1.8. There may be a difference between 1.75 and 1.80. Okay, so how steep this valley is depends on the specific case that we are looking at, and the more the number of grid points, the more the number of n that we have, typically the closer towards 2 that it goes, and the steeper the value of this valley is, okay, the shape of that valley is. So when you are dealing with large number of parameters, large number of equations, then the determination of the optimal value is not a trivial thing. One has to search for it, one has to implement a method of looking for the optimal value into the scheme of solution itself, and that will take extra time, but in many cases that extra effort to find the optimal value is very well worth the effort, because this variation is quite steep. So you could have a factor of 2 or a factor of 3 in terms of the speed of computation when you go to the optimal value as compared to something which is suboptimal. Okay. So this is something that we have to keep in mind when we are trying to implement the SR method.